So that is a cross section and containing the point. And here we interested in calculating the stress at point H and point K here. So what we did, that is a cross section we exposed there, and that is a corner systems. Here the axial direction is X, and the edge is on the north pole, Y, and K. This is K. Z. So in terms of the cross section here, that is here, Y and Z. And what we have last time is we have quite a bit loading here. So here we have the first one is the normal loading, which is getting into the cross section. It gets into the cross section, and that is I think I'm using P, and the value of P equal to 15 kilonewtons. And then we have transverse loading, which is parallel to the cross section, and we use V, and that is 18 kilonewtons. And we have torsion, T, and T we calculated is 0.9 kilonewton per meter. And then we have bending about y-axis and my. My is 0.75, and we have MZ. MZ equal to 1.08. Okay, so now we have five types of the loading. And then for this problem, we want to calculate the stress at 2 points, K here and H here. So we can use the superposition principle, and we analyze the stress due to each type of the loading. Then we can try this. So, for example, the first one, we can try to find the loading at point H. Here, again, I try to tabulate the analysis. So here is the loading type. And then, for example, here we follow up, we have force P and the corresponding stress, and we have either normal stress or shear stress, and we simply analyze this one by one. Due to point loading, and that is our chapter 2, and we know that the normal stress will be equal to the magnitude divided by the cross-sectional area, right? So that is our chapter 2. And for this case, this loading is going into the board, so basically that is compressive. So here we put a minus sign here. And due to the normal loading, they shouldn't have any shear stress, so that is 0. And either you can calculate the magnitude at this moment, or you can leap into the final step, either way, okay? And now the most important is we just write down the steps or the formula, identify that is compressive or tension. And now the second one is we have torsion. So torsion shouldn't have any normal stress induced. And for torsion chapter 3, let me review that one here. So if this is the torsion, if this is a shaft, and say if this is our outer radius C, and then at any locations, for example, that is rho, and we know that the stress equal to, for example, if this is the torsion T, T rho over J. And rho is the parameters identifying any point on the radial distance from the center here. Okay, so for this case, we're using that formula tau will be equal to T, and H is at the radius, and that is C, okay, and using J. And for our example, what is the value of C? I think that one given by the problem. The radius of the shaft is how much?
20 millimeters.
20, thank you. So here, let me label that C equal to 0.02 meter here, okay. And so in this case here, we have all the derived calculation, J equal to pi over 2 C to the fourth power. Okay, now for this one, and what is the directions of the strain stress? And now the direction of the strain stress become important. And for this one, we know that the strain stress at this point basically is tangent to the point, to the circle, and then in the direction of the same circulation of T. So that would be here. So along this line, any point along this radius, that direction of the strain will be like this. Okay, so taking up that one, then the direction of the strain is here. Right, so that's the direction of the tau for this case. So let me do this one here. So for example, here the point H is here, and then we simply just make some symbols, remind us. Okay, this might be used to superpose to other quantities, who knows, but at least we just make a symbol here. And now we go to the next one. So we follow up those kind of the procedure, V, sorry. So V here introduce no normal stress. And what is V? And in our chapter 4, if this will be the transverse loading, and this is the neutral axis, and for example, if along this cut, then we know that this calculation will be tau along this cut will be tau equal to VQ over IT, right? And we know for this case, the direction of the strain stress along this cut will be the same as the directions of the transverse loading. Okay, so using those informations, we know this is VQ over IT. We write it up the equation first. Then the direction will be follow up the same thing. This is point H here. The direction will be going upward. And now we can do a little bit more information. And V is given here. And what is Q? And this kind of our side, the scratch calculations. What is Q? We can make this one here. So for example, if this would be the, say we can make one scenario study. If this would be this circle here, this cross-sectional shape here, and V applying upward. For example, if we want to calculate the strain stress along this cut, then definitely we may choose the shaded area for calculation in concept, right? If we want to know the point here, if we want to know the strain stress along this point, simply we make a cut which parallel to the neutral axis. Neutral axis is normal to the direction of the V. So we make a cut parallel to the neutral axis. That cut bisects the whole entire cross section. We pick either side as a shaded area. And now you look at this one. Now the point is at the top here. So basically we make the cut is really, you can see once this point converging to here, this cut basically approaching to top there. So basically Q will be equal to 0 at point H. Can you see it?
So then
tau will equal to 0. Because the point H is here, you can see if we would select the cut, that would be something like here, right? So this cut will make the whole entire cross section or make nothing. But either way, the Q will be equal to 0.
Could you also think of it kind of like the shear flow way and the way that
the same thing.
Yeah, like because of the way.
If we take the shear flow, then the shear flow only is VQ over I. the same thing. We have to resolve the Q
And like
first.
if it's in line with the force, like remember how we drew the little
Yes,
arrow?
yeah. So for shear flow, we still have to deal with Q first. Okay, so either way, so for this example, say if the point is here, once this point converging to edge, you can see basically the shaded area disappears. Okay, so at point H, Q equal to 0. So this way is not much to say this will be equal to 0. And now we go to My. My, for the bending, for example, if this is the front view, and this is our neutral surface, if the bending is like this, and we know the distribution of the bending stress, which is normal like this, and M, so this is our y-axis, this is our x-axis. So at any point, if this point has a distance from the coordinate, okay, so y, so basically sigma equal to minus my over I. Using that equation, so here we, for the bending, we have no shear stress. So here is, we take this formula. So my right now is like this. So my, let me draw that one here. So this is the cross section. So this is our y-axis, this is our z-axis. My is acting like this. And here, this is a point we're interested. So we know the formula is minus my over I, right? So for this case, the point is exactly onto the neutral axis, right? So here, the y equal to 0. Why? We can do this again. Let me make one example. If this is rectangular, and if this is a y-axis, this is a z-axis, and this is my. For this example, we know that which portion is in tension? 1, 2, 3, 4. Which portion are in tension?
That side.
Left side. Okay, this is in tension, this is in compression. How about this point?
Well, it's in 0.
0, right? So the same scenario like this. Okay, so that is 0. And MZ. So MZ, let me draw this one here. Y-axis, Z-axis. And MZ is in this way. So now the point H is here. So respect to MZ, where is the neutral axis? Which means this one. This is the neutral axis. Okay. So for this case, again we put into this formula, and M, the magnitude, and the distance, what the distance from the point to here, right? So that is C. And I is a moment of inertia respect to the z-axis, and which is pi over 4 c to the fourth power, right? And then H locate in, we have top and the bottom, which area is in tension, which area is in compression.
Tension's on the bottom.
Tension at the bottom, right? So here is in compression. So here the point at here should be negative compressive. Okay, so now we have everything here. So therefore we take the summations. Sigma will be total equal to the 3 terms, the 1, 2, 3, 4, 5 terms plus together. So that will be equal to, let me use the red color here. So that will be equal to compressive due to this one, and then this is compressive, mz, and times c, pi over 4 c to the fourth power. And those one, PA, MZ, whatever, those are numbers, only magnitude. So we plug in here, that number is minus 183.8 MPa. And here, do your calculation carefully, okay? So that's the magnitude, and that minus sign tells us at point H that is in compression, in compressive normal stress.
And this already, yeah, this all accounts for sign convention too, right?
Yes, and again, here the P, MZ, you simply plug into their magnitude as we indicated. Because here already we have tell the sign in our formulations. Okay, so here we simply take the algebraic summations of those, whatever the number, negative or positive. And now we take the summation of the tau. So here for tau will be equal to this one plus this one plus this one plus this one and plus this one equal to this one here. Okay. So the 5 terms plus together, they only have this term. So tau will be equal to Tc over J, and the magnitude, plug in all the things, they now be 71.6 MPa, and the direction is going left. So here, here the direction is very, very important. So let me try to highlight a small cube. Yes.
Is that for both of them, or is it just specifically for that tau section?
Specific at H. Localized, those are the localized, the local information around H. If we move away from H, then we have to repeat. For example, say, if I ask you to calculate point here, okay, so for example, let me call this is J. At point J here, then you have to repeat all the calculations.
Okay. What about sigma then? Where's
sigma here,
no,
the same.
Where's the direction of sigma then?
The sigma is compressive.
But no, I mean like if tau has a direction of that, is like sigma going?
Sigma, let me ask you, so this is our cross section. Sigma is negative, so what's the direction? We talk about is this cross section, the normal stress to this cross section into the board.
Yeah.
Right? We compress the cross section so that sigma go to the board.
Okay.
Okay. And then let me use a small cube to say, for example, around point H here. Let me highlight. Let me use this block. Okay. So I want to highlight a drawing. So this is the shaft, like this, and point H is here. Okay, and then you pick a small cube, and I want to show the direction of the stress. And say, for example, around here, so I pick this one. Okay, so let me highlight this one. So basically this, the front side is part of the whole cross section. So hopefully you know what I'm showing here. So here is a cube. Let me highlight that one. So here is the cube. And this is part of the cross section. So this is part of the cross section. So the cross section is so huge. Okay, so hopefully you know what I'm saying, what I'm drawing here. So the point H is here. Okay, that's the point H. And this cube, and you have to make it very small because the information is local. So the distribution of the stress is like this. The first one, we have the normal stress 183. So that will be the normal stress to this cross section. So the 183 is go into 183 sigma. And on the opposite side, they have the same thing, sigma 183. The shear stress is on the top of the edge going that direction. So the shear stress is on the top surface here, on the top, lying on the top surface and in that direction. So this is tau. Yes?
What values let us know that it's going left? Like what?
Huh?
How do we know that it's going left?
Because of here. Because of, I'm showing here.
Oh,
Okay. Okay. And then using our chapter 1, in chapter 1 we know that if this is the 2D element, so if we would know the tau like this, then on the other three sides, right away we know in equilibrium the stress must be here. So given tau is like this, on this side the tau should be here, and on the opposite, the side and the bottom side, you can draw the direction like this. Okay? Okay. So usually, in terms of the convenience, sometimes people just like to say, instead of drawing 3D, they like to use the 2D to represent everything. So for example, the people just pick up this front side as the 2D element for displaying the distribution of the stress. Oh, sorry, I picked the wrong side.